Why are metrics? Let's talk about the fourth chapter, distribution user analytics. In this chapter, we talk mainly about why metrics are important. So, why metrics are important? Intuition alone is seldom adequate to make a decision about user or to get insight about user in web analytics. For that, we need data. Data helps to inform those intuition about user behavior in web product. And also, secondly, data helps to refine our intuitive sense such that we can provide better value for our users. If we depend on our intuition, there will be some wins and losses. However, we will depend we will from our own experience, what we can say is that even though there are wins and losses, will be mostly focused on wins, and this will make us biased to our wins, which will paint a wrong image of our ability. Metrics can help quantify phenomena, but all phenomena cannot be easily quantified. There are some complex phenomena which are notoriously hard to quantify. Like now let's take example of a ball game. So let's say we are outside a ball game and we are trying to figure out what's happening inside a ball game, inside a stadium for where the ball game is being played. We can hear some cheers and claps, and from that we can make sense that who's winning the game. But even best of us can predict sometime who's winning the game, but even best of us will make some mistakes. Now, getting metrics is like going inside a game and being able to see who's winning the game on a scoreboard. Now let's talk about statistical tools for metric development. Before we do that, we have to understand some statistical foundation core concepts uh, to understand to do the metric development. The first is distribution. Distribution is a bell curve where the middle of the curve is really tall and tail of the curve are are smaller in height. And it says that at the middle, the frequency or number of count of population having certain dimensions, or let's say height, is really huge, while count of people who have extreme heights, really small heights and really tall heights, are low. So this is a bell curve. Now let's talk about exploring a distribution. So bell curve or this normal distribution is a listing of all possible values in order of fashion, and each value in the x-axis shows how often the value occurs. In comparison, the metric is aggregated value or aggregated measure of the distribution. It's a single value that informs about the distribution. Now let's take example of a budget, household budget. Let's say we have the budget of monthly spending for last 12 months. You will have a 12 data points across x-axis, and it will show that the total amount of spending for each month for last 12 months. And some month there will be more spending, some month there will be little spending, and some month there will be no spending. And if you look at this example, the aggregate value of this distribution, let's take mean. It will be the value that represents the average spending throughout the year. Now comes the mean, median, and mode. These are a aggregate measure or metrics. Distribution metrics are important because human beings are not able to remember the hundreds of data points. An aggregated measure helps us to understand or get some sense about hundreds of data points from which we can keep track. These are called statistical moment. Mean is a first statistical moment, which is calculated by summing the values and dividing by count of those values. Summing all the values and dividing by count of the all the values. Now let's take example of the Golden State Warrior. Heights are the five people of the. Let's take example of a Golden five heights of the five-player Golden State Warrior, where we have the warrior, we have the players with different heights. Some are tall, some are some are really tall, some are like 5.6 heights. There are different people with different heights in the Golden State Warrior. And mean of this height of this Golden State Warrior will be summing all the heights of the players and dividing it by count of the players. Mean can be misleading sometimes because if data is skewed or, or the data is some of the multiple distributions. Second is the median. Median is calculated by arranging all the values in the some order and calculating and picking the middle value, or if there are two middle values, then if there's no one single middle value and getting the unique count. If there are two middle values, then summing those two middle value and then dividing by 2. That's the median. Now let's take example of basketball player. Let's say there are like a six basketball player with a different heights. We arrange all the basketball player in the according to the heights from descending to ascending order, and we pick the middle height. Mode. Mode is the most frequently occurring value in distribution. In a normal distribution, usually mean is equal to median mode. Now let's say we have the distribution of the height of the NBA players, which is a normal distribution. The middle value is a mean, which is equal to height of all the players. Now let's say there are other distribution beside normal distribution. In that, mean is not equal to median mode. And usually when the distribution is skewed, in practically, median is a better indicator of the distribution than mean, because median is not impacted by any skewness. Variance. Now let's talk about variance. Variance, the definition of variance is it indicates the spread of the data. This is important variance because all data sets are not equal. Some data sets have more dispersion than others. Let's take, for example, the world population. The world population is really spread out. The height of the world population is really spread out. Some are 1 feet and some are 8 feet. But let's take the spread of the height in basketball, NBA basketball team. The shortest of the height is 5, 6 feet, and it can go to what 7, 7.5, or 8 feet. So the spread is not big in the basketball team. Now, variance helps to see whether our estimate is closer to truth. The smaller the variance of the mean of our estimate, we can say that we are closer to truth. At the same time, if there's a large variance, then we can say that our estimate is off. Usually, variance comes from two different sources. First is either the true spread of the population or our sample size is really small. Smaller sample size usually generally leads to larger variance. Sampling. This is a really important topic. Sampling is taking a subset of data from the full population to estimate some metric about that population. Usually sampling can be done with or without replacement. Sampling with replacement is once we take the sample, that item will be put back into the sampling pool. Sampling without replacement is once we take out that once we pick that particular item, it will not be put back into sampling pool. Let's take example of the hat with the different balls of different color. Now, when we sample, we pick a ball of some color. In sampling with replacement, once we pick the ball, we put back in that ball into hat. But if we do a sampling without replacement, once we pick the ball, we will not put it back to the hat. Sampling with replacement does not change the distribution after sampling is done. But sampling without replacement will change the distribution once sampling is done. Bootstrap sampling. Bootstrap sampling is different than regular sampling because in bootstrap sampling, instead of taking one small sample, we do multiple small sample many times. And this is a sampling with replacement. So let's say there's a team of basketball players, and we are trying to estimate the mean. What we do is that we take a small sample from basketball players, measure the mean, and we do it many times. Let's say 100 times. We take 100 samples and we calculate the mean 100 times, and we calculate the variance in that mean. This variance of the mean is called standard error. Other measure is skew. Skewness is whether data is skewed, whether we have like lopsided data, either data is mm, either we have data that is we have bigger count of data that is to our left or left or right extremes. Slope. Slope indicates whether we have the slope of the point of the curve at any given point. Kurtosis. Kurtosis is the fatness of the tail at the edges. Now let's talk about exponential distribution. Exponential distribution is really important distribution for user analytics. Now let's take example of a product where there are views on particular item in a feed. What we see in the real life in practical is that the earlier post has the higher number of views than later post. The earlier post in the feed the posts that are at higher top have a more number of feeds, have more number of views than posts which are at a down. So what happens is that people usually see the view the post which are at the first and they ignore the rest. This is usually see in the social platform where there are lots of feeds. Identifying your data to see if it has exponential distribution is really important. So let's say we are experiencing in a web platform, we are experiencing that from our analysis of user purchase, we see that if there's exponential distribution data, we see that some people are making lots of purchases and others are making little or no purchases. This can translate to that few posts are getting lots of views and other posts are getting none or really few views. In exponential distribution, mean and median are not same. The mean is better identified in exponential distribution than mean. Now let's talk about, and lastly, let's talk about bivariate distribution. Bivariate distribution is about relationship between two variables. The two variables can be either positive related, negative related, or completely unrelated. Positive related. Now let's say positive related means if one variable increases, other variable also increases. The example is the height versus income. If you look at the example of NBA players, if we plot the height in x-axis in ascending order and plot income in the y-axis, we see that as the height increases, the income also increases. Negative correlation. Example of this is when not definition of this is if one variable decreases, other variable increases, and vice versa. The example of this is the size of the class and the quality of education or scoring in a test. Larger the size of the class, the lesser the scoring in a test. Completely unrelated. The one variable does not affect other variable. The example of this is the temperature in Mozambique and the price of stock. There is no correlation between these two. So, I just talked about why metrics are important and some statistical tools for metric development.